And we're back with example number 4. Okay, so I like this example because it's kind of quirky, or you might think it's kind of quirky in terms of the solution that you end up getting. I added a 6 kilonewton compressive force out here at the edge, just so that we finally have a normal force, because on most beams we don't have a normal force, but I like to show that they can exist. So here we are pushing on here. Okay, so again, you guys stop the video, draw your own free body diagram. Okay, and then check your free body diagram, stop the video, calculate your reactions, and then you come back on here to check. So if you want to pause right now, go ahead and pause. I like to just, again, I know I say this all the time, you should never have a wrong answer in statics because the sum of our forces always equals 0. It doesn't matter where we sum moments. The sum of the moments has to equal 0. So I found my reactions by summing moments about the other respective reaction, and then just checked my forces in the y direction. Okay, so we are going to work this problem looking at both the left and the right. Okay, so if you are ready to go, again, when we cut a beam, we can't just cut it wherever we want. We can't cut it into 12 different sections. We either have to cut it and show all of the left or cut it and show all of the right. And this applied moment is just to the right of our cut, so it will be included on this part of our beam. Okay, so you guys can stop your video if you want. I'm going to continue, and I'm going to draw a free body diagram of just the left. And I know that AY was 48 kilonewtons. And I could have a normal and a shear and a bending moment showing positive beam notation. And I also see that I have a uniform load, and this time it is actually the entire amount of that uniform load. So we know that that 48 kilonewtons is acting right back down at A, and we are at 2 meters and 2 meters. We also have that X component that we found going to the right. I don't know why I put an X there because I said X component. It should be 6 kilonewtons. So now when I sum my forces in the X direction, I'm going to have a positive 6 plus N equals 0. My normal is a negative 6 kilonewtons. I leave it as a negative. That tells me it's compression, which makes sense. If I'm pushing this way, I got to be pushing back equal and opposite to stay in equilibrium. Pushing back in the middle, right there, is compression. We can sum our forces Y equals 0. So I have a positive 48 minus shear equals 0. My shear equals 0 in the middle of the beam. Can that happen? Absolutely, it can. We can go from positive shear to negative shear depending on where we're looking at our cuts. And if we're going from positive to negative as we move down the length of the beam, at some point we have to be at a shear equals 0. Okay? Because we're going from positive to negative or negative to positive. Now I'm going to sum the moments about my cut. And again, I like to go right around that cut, and I start at the left, move forwards. So I'm going to have a minus 48 kilonewtons times 2 meters plus 48 kilonewtons times 2 meters plus my moment equals 0. So I also get that my moment is 0 right here at this cut. Can that happen? Absolutely. I can be going from positive moment where I have this kind of curvature to a negative moment, okay, where I have this type of curvature, and this is where my moment equals 0. And it's also called an inflection point when you move into strengths and structural analysis. It's where we change curvature. It's where we change behavior from positive to negative. And so, again, that's okay that that moment equals 0. It's just telling us that we have a transition happening in that part of the beam. And it doesn't mean that it's 0 all the way across. If you wanted to go back and calculate the moment here, 1 meter in, you would find you actually had a moment. Okay? So now let's just go ahead and cut it from the other side. So this might be a good time for you all to pause the video and set up your own free body diagrams and make sure that you have the correct positive notation in terms of our assumption of behavior. And we have 2 meters and 2 meters. So this is the right half of my beam, except that I'm missing this applied moment of 24 kilonewton meters. Okay, so I should get the same answers because it's at the same part. Forgot to box my answer. I am going to start at the right side of my beam, the left side of my beam, and move to the right. And I'm going to sum forces in the x direction. They equal 0. Now, I'm assuming positive normal force. Normal force is that perpendicular force to our cross section. I'm assuming it's in tension. I'm assuming it's a tension member. But when I make my sign convention for summing forces, it's a negative because it's going opposite of the direction I'm assuming to call positive. Okay, we come across and I have negative 6 kilonewtons equals 0. So I find that my normal force is a negative 6 kilonewtons. Okay, which is compression, and it's the same answer we got here. If you like to be weird and maybe call to the left positive, then I would see I'd have a normal plus a 6 kilonewtons equals 0. I would still end up with a negative 6 kilonewtons. That's why positive beam notation is behavior. You can have your sign convention down here whatever nutty way you want to do it. I just kind of am like to the right is x or positive, to the up is positive, just so I don't confuse my own brain. Okay, we can now sum forces in the y direction, and I have a positive v plus a 12 kilonewtons minus a 12 kilonewtons equals 0. So again, I get my shear equals 0. And again, I can sum my moments at that cut. The sum has to equal 0. So I have a positive behavior, but according to my right-hand rule, it's a negative moment. Okay, and then I come just past that cut, and I have this applied moment of 24 kilonewton meters. And I need to know, is this a positive moment or is this a negative moment? Okay, so you guys know, I'm really weird. I'm going to draw my cut, and I'm going to draw just right here, like a millimeter, right at my cut. And I'm going to show that I have this external applied 24 kilonewton meters. So if at this cut, just looking at this applied moment, it needs to be in equilibrium, I know that my internal has to be equal and opposite. Okay, otherwise we would have rotation. I'm moving too fast for the camera. But now when I look back, is this a positive moment according to my behavior or a negative? It is indeed a positive moment. So I'm going to add a 24 kilonewton meters. Okay. Then I have plus 12 kilonewtons times 2 meters minus 12 kilonewtons times 4 meters. Sorry, it's so smushed. All of that has to equal 0. And I'm going to move my moment to the other side to make it positive. And then I have 24 plus 24 minus 48. My moment at that point is indeed 0, which is the same answer I got working from the left. So if you guys need extra practice, if you don't feel like you're picking this up quickly enough, or if you feel like you're still very slow in drawing free body diagrams and writing equations, at this point you should be pretty comfortable with drawing free body diagrams and writing equations. And if you feel like you're really still struggling in being quick and precise, then work these problems both from the left and from the right. Because again, in statics, you should never, ever have a wrong answer because you can always approach the problem from a different angle. And because nothing's moving, the sum of the forces are 0, you will end up getting the same answers. So again, if you are struggling at all, I would say take some of these problems and work them forwards and backwards and forwards and backwards and forwards and backwards. Okay? My next videos that will be coming up are going to be finding internal shear and moment equations, which right now we've just been looking at a point in space that we're finding internals, but really I need to know all the way down the length of the beam what my shear and moment looks like, because that's how I'm going to be able to design for those maximum values of shear and those maximum values of moment, both positive and negative. So instead of trying to cut the beam into a million little pieces and do free bodies and equations over and over and over, I can actually draw a picture of my system. So that's up next. See you guys.